Hi, I'm Selva Prabhakaran. In this one, let's understand why R square is a problematic regression metric. Now, in order to understand this, first you will need to understand the intuition behind R square, the formula behind R square. We will tackle that first and then come to the problem of why R square is a problematic metric. Okay. To understand this, let's do it with an example. Say you have the data for housing prices. The Y here represents the housing price values. We have this data set. And you also have various information about the various houses, such as the area of the house, road width, number of schools, so on and so forth. You have multiple different variables. Now, with this data, you can build a regression model, say Y as a function of various different X variables, area, road width, so on and so forth, right? If you build a linear regression, you will get a formula that looks something like this. These are the beta coefficients and the respective X variable values. And finally, you have the error term. Now, for the sake of understanding, let's pretend that you have just one single variable. Let's cancel all of these out. Okay, error can be there. Now, you have this. We are simplifying this to ease our understanding into just one single X variable. So, Y is a function of X1, beta 1 X1 plus the error term. Let's imagine the X1 that we have here is the area of the house. We have the area of the house on the X-axis. For various different values of areas of the house, you have the corresponding values of the housing prices. So you have this information. Now, if you are going to fit a linear regression model, the whole purpose of this linear regression, you will get an equation out of this, right? You will get equation means you will have the linear regression will predict the value of beta 1 out of this. Alright, that's the output of linear regression itself. Once beta 1 is predicted, you will be able to make this line of best fit that we have here. This line of best fit represents the predicted value of the housing price for various values of the area of the house. Suppose the area of the house is this value. Alright, we will substitute, say this is say 500. Alright, 500 square feet or something like that. We will substitute this X into this equation. We already have the linear regression will provide us the beta value here. So you multiply both of this, 500 multiplied by the beta, you will get, so it will go and hit here. This point along the Y, this point, the value of Y is what this equation helps us to predict. Alright. So for various different values of X, this line of best fit represents the predicted value of Y, while we have the various actual values as the actual data points here. Okay, this is what linear regression does. Now, what would happen if we have a perfect linear regression? What I mean by that is, now here you have the predicted values, but the actual values are not falling exactly on the line. There is some amount of residuals left. There is some amount of inaccuracies left over in the model. And this is desirable here in this case. If there is no residual at all, if the model is perfectly predicting every other house for this particular data, all right? If it is perfectly predicting, you will get a line that might look something like this. It could be a straight line joining all these points, or it could be a curve like this. Linear regression will not be able to do this, by the way, but that is a different story. But if you get a perfect prediction, this is what we refer to as the overfitting, all right? This is a case where the model would overfit and give us a highly skewed prediction. So if the value of X is over here for this particular value, if it was the line of best fit, the predicted value would be somewhere over here, and this point would represent the predicted value. But here, this curved line here represents the predicted values of Y itself. We represent the predicted values as Y hat. Now this is where R square comes in, wherein the R square of a prediction, a fitted line that looks like this, will have a perfect 100% R square. Alright, we will talk about what R square represents shortly, but this will have a perfect 100%. Whereas this curve, which is more, this line of best fit, which is more desirable, will have an R square that is far less than 100%, far less, maybe 75%, 80% and so on. So what does R square represent? R square tries to explain or tell us what proportion of the variability in Y does the model explain. Now, what do we mean by the word variability in Y? Variability in Y. So what does this mean? Let's understand that this is an important concept. Now, say you have a data that looks something like this. You have for various values of X, as X keeps on increasing, the value of Y remains the same. The value of Y is a constant. Now, in order to make a prediction for Y for this particular this kind of data, we don't need a model. Because the value of y is constant, suppose this value of y is 10, we just need to say that for whatever value of x, the value of y is going to be 10. This is just a constant. This means there is zero variability in this kind of a data set. On the other hand, look at this. As x increases, the value of y also increases, but it is not increasing linearly like this. There is some amount of variability that happens, isn't it? This is the information that is contained in y. We want to explain, like, as x increases, what is it? How can we build a model that can predict or explain x so that we are able to predict y with just the value of x? Now, this is exactly what R squared tries to answer. The variability explained by the model, this is the numerator, divided by the total variability in y. Variability explained by the model divided by total variability in y. How do we understand this? I will come to that, but you need to understand the total variability explained by the model plus the variability unexplained by the model. Okay, there is a total variability in y. Okay, we will come to the formula for this. The total variability can be broken down into variability explained plus variability unexplained. Okay, these two add up to total variability. With that in context, let's understand how to calculate total variability, how to calculate that. Okay, let's imagine you have a variable y. These could be any values, various different values of y. Okay, imagine whatever value you want. Let's say this is the area of various houses we have in the data set. Okay, so you have this data. We will be able to compute a mean value for this. For this data, we'll be able to compute a mean. We add up all these values, divided by the total number of observations. That's the mean, right? Now you have this data. Now create a hypothetical y dash where each and every value here is nothing but the mean of this particular value, mean of y. Okay, you substitute this and put this value in every other cell. What would happen now if you sum up all these values here, and if you sum up all these values in this y dash, both of them will be equal, exactly the same, isn't it? This is foundational mathematics. Now, if you translate this into form of x versus y, all right, x can be simply as simple as 1, 2, 3, 4, 5, 6 here in this case. Okay, it's not the actual variable that we are talking about, just 1, 2, 3, 4, 5, 6 index. Here, the mean of y, you plot this is y dash. This particular set of values is y dash, okay, and plot y also here, okay. Now, if you take this differences between the mean of the y, right, mean of the y is having the values in y dash, isn't it, the mean of y. So, if you compute these differences and square them up in this type of a formula, so yi minus mean of y everywhere, this value is going to be the constant. So, we sum up, we compute these differences, square it up and sum them all up. That would be the total sum of squares, which is nothing but the total variability. So TSS means total sum of squares. Likewise, let's also understand the variability not explained by the model. How do we get that? Not explained is the part, say you have these actual values. You have the x and you have a y and you have various different actual values here, isn't it? And you have the line of best fit running here like this. For various values of x, the predicted value of y is represented along the line of best fit. Okay, these are the predicted values of y. Now, variability not explained is we want this line, the predictions to be very close to these points. Okay, but the predictions are on the line. This gap, the residual perpendicular distance along the y-axis is nothing but the residuals. We call it as residuals. These residuals represent the variability not explained. Okay, you take these residuals, compute these residuals, square them all up, square each of these residuals and add them all up. Okay, square, I think that this is getting hidden. So yi dash minus yi the whole square. All right, then sum it all up for I equal to 1 to n for all the data points. This observation, this formula represents the variability not explained by the model, which is nothing but the residual sum of squares. Now, coming back to the formula for R square, we initially described this, right? R square is nothing but variability explained by total variability. And we also know that variability explained plus variability not explained equals to the total variability. Okay. We just saw the formula for total variability, which is the total sum of squares. We also saw the formula for variability unexplained, which is nothing but the residual sum of squares. Okay, but we have variability explained in the numerator. So to get this, we move this to the right hand side. So TSS equals to TSS minus RSS, right? That is nothing but variability explained. That is the numerator. Divided by the total variability, which is nothing but TSS. So this becomes 1 minus RSS by TSS. This here is the formula for R square. Now, if you do the math, substitute the values into this formula, 1 minus RSS by TSS. We know RSS is the residuals, the predicted value minus the actual value, sum them all up and square them all up and then do the sum, right? Likewise, the actual minus the mean. We compute this difference, square it, sum it up. This whole term is nothing but the R square values. I hope now you are clear with the intuition behind the formula for R square. That is clear, right? Now, what is the problem with R square? If you are evaluating your machine learning models, especially the linear regression models, especially, this is where R square comes into picture most of the time, right? If you are going to say that, say you have a linear regression model that has a R square of 80%, you have another linear regression model where your R square is 95%, it doesn't mean that R square of 95% is better than R square of 80%. Okay, you probably know this. Because it is going to cause this. We are encouraging overfitting in this process. This is a very, very key thing that you need to understand. Don't go for a model that is always having a higher R square. That does not mean a lot whenever you are going to the process of selecting your models. So look at this kind of a model here. So you have this data looking like this, an R square of 77% here, whereas this would have an R square of 100%. This is not at all desirable in any case. Alright, the second reason is, this is the main reason, R square always increases as you are keeping on adding more variables. I will tell you what happens. Say you have a model Y, but try to predict the housing price as a function of 4 different X variables. Okay, you have built a model like this. Now, on top of this model, you introduce another random variable as additional feature or predictor to the existing set of predictors. You are introducing this, you are building a new model, and you are getting a new R square value of R2 square. Okay, this is the original R square, R1 square. Now we are getting a new, slightly improved or slightly different or increased value of R square value. So that we are calling as R2 square. Now the thing is, this R2 square will be always greater or equal to R1 square. R2 square will never be lesser than R1 square. This is for sure. Now why is this the case? Because linear regression, typically the OLS regression, ordinary least square regression, will work in such a way that since the original variables are present here, right, x1, x2, x3, x4 tries to explain a certain amount of variability that is present in Y. Okay, now you are introducing a new variable here. It will decide the coefficients of R in such a way that it is trying to improve what it's already having. In the worst case scenario, if this is completely random, there is no pattern absolutely in R1 whatsoever, it will try to make the coefficient of this particular newly introduced random term as 0. As a result, remaining coefficients will become unchanged, and your R2 square value, R2 square, will be equal to R1 square. That's the worst case scenario that could happen. But typically, there might be some patterns that's existing in this new variable. As a result, it tries to make use of this new variable also. Thereby, the R2 square will be slightly incrementally greater than R1 square. So that is why all the regression packages will give you the adjusted R square in addition to the R square, because adjusted R square will penalize for the number of predictors that you have in the model. Alright, it is possible, say you have, previously we had 2 models, 1 and 2 different models, right? Where Y is a function of x1 to x4. Alright. Second model was Y is a function of x1 to x4 plus it had a random part. Now, when you are using adjusted R square, it is possible that this model will have a lower adjusted R square than the first model. That is possible. Why? Because in the denominator, you have a P constant here. The P here represents the number of predictors. So for a new model, if you introduce one additional predictor, this denominator value is going to go down, okay? As P increases, plus 1 means this whole value is going to go down. If this part goes down, this entire term is going to increase. This entire term is going to increase. If this entire term is increasing, 1 minus this part will be a smaller value. So by introducing a new variable, the adjusted R square value will go down net. So that's why always look at adjusted R square when you're comparing models instead of R square. This is very, very basic. So this is a very popular interview question. Why adjusted R square instead of R square? Also, why R square is not going to be always useful. This is also a very important thing to understand, and explaining the intuition behind the formula for R square is also a very fundamental concept that all data scientists must know.